Point two, we'll take a look at um, vertical linear problems using Newton's second law. Sum of the forces is mass times acceleration. We'll look at these using our forces, um, and then later we'll use energy to solve some of these problems as well. So there's multiple ways to actually do it, which makes it kind of interesting. Um, the first type we're going to look at are elevators. So an elevator is just a rope pulley system pulling up a person that's traveling upward. And so let's imagine this person, though, like standing on a small scale so that there's a support force pushing upward on there. So if we think about, we could draw a free body diagram for the whole car system, car and person all together, and then that would have a large FG down and a tension up in the cable, like that. If we did a free body diagram for the person, if this is for if they're at rest, well, then we have an FG down, and the upward force is this F perpendicular, which actually, that is the scale reading. So that comes from the scale. The tension in the cable supporting an elevator controls the motion of the cab of the elevator, but the passenger's motion is governed by the normal force provided by the floor of the cab. So the person is just standing there, the cable tight, when you push like number or floor 8, say, you get in on the bottom floor, then the cable tightens up and the car begins to rise and catches the person going up. Okay? It's the same sort of process that in the snowstorm of last night, I was pulling my 5-year-old around the block and the sled, and we would pull forward, and then I would stop the sled, and she would slide forward. She'd be at the front of the sled, and then I would begin to pull the sled quickly, and then she would stay in place. Her inertia would keep her there, and then the sled would move along and slide up until the back of the sled would catch her, and the whole thing would move together. So the cable car, the elevator car, starts moving up, and it takes the person up for him. So it's a normal force provided by the floor, which we can measure with a Bassam scale. So we can say about the motion of the elevator, if this scale reads the passenger's true weight, what can we say about it? Okay. Well, in that case, if the scale reads the person's true weight, then we know by the free body diagram that F parallel and FG are equal. It's in equilibrium. Okay? So in that situation, it must be either at rest or moving at constant velocity. No acceleration, zero acceleration. So it could be just sitting there, or it could have accelerated up to a certain speed, and now it's just keeping that speed. But at that point, the scale is going to read the true weight. Oops. Oops. I gotta, sorry. What the heck? I wanted to undo it. Kind of a pain, sorry. Okay, so now what can be said about the motion of the elevator? The motion of the elevator, if the scale reads the If the scale reads the passengers, it reads more than the passenger's true weight. Well, the free body diagram in that situation would be Fg down, but since the scale is reading more, then F perpendicular is bigger. So in that case, the sum of the forces is mass times acceleration, and the winner is F perpendicular minus Fg equals mass times acceleration. So if we must, in that case, have an upward acceleration, so our acceleration is up, and that could mean a couple of things. It could mean, first off, that we are increasing our speed upward. Or accelerating up. And then secondly, the other thing could be we could be decreasing our speed going down. Or a negative acceleration. It would be a negative acceleration because it would be up and we're moving down. Or the acceleration would be positive and we're moving in the negative direction. But we would be decreasing speed going down. So think about that for a minute. So it could be that you're on the bottom floor and you press floor number 8 and the car starts to pick up, so it starts to accelerate upward, and because of that, your weight would actually show on the scale. The perpendicular force of the scale would be higher, so the scale would read higher during that acceleration. Well, the other thing could be that you get in the elevator and you start going down. You pick the lower floor from one of the higher floors. You start going down, and then as you get towards the ground, you start to slow down, and that would cause the floor to push up more than in the scale to read higher. So those are the two situations. Give that some thought. Here's the other example, which would be, well, we say if the scale reads less than the true weight. Less than the true weight. Well, in that case, we have the fact when Fg is bigger than F perpendicular. So in that case, the sum of the forces equals mass times acceleration. Fg is the bigger of the two and we would be accelerating downward. Okay, we'd have a downward acceleration. We can have a downward acceleration if, one, we're increasing our speed down. Or two, if we're decreasing our speed going up. Both cause a downward acceleration. So take the case of increasing speed going down. You're at one of the top floors and you get in and you press ground level and you start to increase your speed going down. That would cause the scale to read less because the whole car is moving down. The floor is not going to push into you as hard. Or the other option would be you get in at the ground floor, press floor number 8, and you start to go up, and then as you get towards floor number 8, you start to slow down, so the scale is going to read less because you can continue as you keep in motion going up, but as the car slows down. Okay. Now, what would you say if the scale actually read 0? That would mean that the free body diagram was all FG, and F perpendicular was 0. If that's the case, then your acceleration is actually 9.8 meters per second squared, and you're in free fall. The cable's cut, and you've got problems. So, anyways. So let's look at this math problem. A 65 kilogram person is riding on an elevator. The bathroom scale he is standing on reads 400 newtons. What is the elevator doing? So in that case, you have an FG down, okay, and an F perpendicular up. And this F perpendicular is what the scale is reading, which is 400 newtons, and FG would be 650 newtons. And what you would do is the sum of the forces equals mass times acceleration. But the winner is FG, and the loser is F perpendicular equals mass times acceleration. And FG is 650 newtons, and F perpendicular is 400 newtons, and the mass is 65 kilograms times A. So 250 newtons over 65 kilograms equals A. So A would be 250 divided by 65 would be 3.85 meters per second squared. And this is down because I can tell from my larger winner was FG and the loser was F perpendicular. Now the fact that it's down means that he could be increasing his speed going down or increasing his speed going down or decreasing the speed going up. Another type of vertical linear problems is the Atwood machine, one of the simplest machines. And I'll ask you to remind me in class to play the Murphy's Law song about a pulley system for you. So if you'd remember to remind me, that would be good. But an Atwood machine is just a pulley over which a string is passed and connected. Okay, yeah. With an Atwood machine, the pulley system, and one mass connected to another larger mass. Say 20 kilograms and 12 kilograms for an example. Now, because the one mass is higher, if we ignore the friction in the going around the wheel between the string and the wheel, the pulley system there, the one mass being higher is going to produce an acceleration in that direction. So the masses are attached to each other. They must move together. They move in opposite directions, but the magnitudes of their displacement, velocity, and acceleration must be the same. We'll continue to use our massless, frictionless pulley, so there's only one value of tension in the connecting string. If the masses on each side were identical, nothing would happen. They would just sit there. The greater the difference in mass, the bigger the acceleration. As long as the masses are non-zero, the acceleration cannot be equal to g, and it can never, of course, be greater than g. So we'll look at tension forces, accelerations, and masses in these blocks. And the best way to do it is through an example problem, which I'll do for you now. So with free body diagrams, you could see that the FG down here for the first block, this one, is bigger than the tension going up. And we'll stop there. I'll do the rest in class.